All right. All right, and we're back for discussion 2-3, Advanced Periodic Trends. All right, so the first thing I want to look at is some interesting patterns we see in ionization energy. So what we've got here is ionization energy data for the elements going across period 2. So we see it goes from lithium to neon, and just like we would expect, we see the ionization energy generally increasing. There are two notable exceptions here, though. One, between beryllium and boron, where we see the ionization actually decrease, and the other between nitrogen and oxygen, where we see the ionization energy also slightly decrease. Now, both of these exceptions can be explained with the electron configurations of these elements. So if we look at the discrepancy between beryllium and boron, we see that beryllium's outermost electrons are in the 2s sublevel, and that sublevel is completely full. And if we look over here at boron, we see that boron also has a full 2s sublevel, but it also has one electron in the 2p. Now, what we get is a slight increase in shielding from this full s sublevel, so this 1p electron is actually easier to remove, and so we'd see slightly decreased ionization energy. And if we look at the trend from nitrogen to oxygen, we see that nitrogen has 3 unpaired electrons in the 2p sublevel, whereas oxygen has one set of paired electrons. Now, once those electrons begin to pair up, the additional electrons being added increase the total amount of electron-electron repulsion, and so they're slightly easier to remove. So here are the reasons for that. The boron exception is caused by the addition of a p sublevel, which causes a slight increase in shielding. And the oxygen discrepancy is caused by electron-electron repulsion when the p electrons pair up. All right, so second, third ionization energies. So when we talked about ionization energy in IB Chem 1 and in the pre-Unit 2 podcast, we were actually talking about the first ionization energy. Excuse me. And the definition of first ionization energy is the amount of energy required to remove one electron from an atom in the gas phase, or the amount of energy required to remove 1 mole of electrons from 1 mole of atoms in the gas phase. So second, third, fourth, fifth, etc. ionization energies are just the amount of energy required to remove the second, third, fourth, fifth, etc. moles of electrons from a mole of atoms in the gas phase. And successive ionization energy data can actually be used to predict the group in a periodic table that an element will likely belong. So take a look at this problem, pause the video, and see if you can work out which group this particular atom belongs in. All right, so when I look at this data, I see the first ionization energy is 900 kilojoules per mole. The second ionization energy is 1,760 kilojoules per mole, and the third is 15,000. So we see a really large jump from the second ionization energy to the third. Now that tells us that this element will belong in group 2 because we see that huge jump after the second ionization energy. So if we look at the periodic table, all the elements in group 2 have 2 valence electrons. Now, magnesium, for instance, can lose 1 electron rather easily, and it can lose the second electron very easily. But once it has lost those 2 electrons, it will have a noble gas electron configuration. In this case, the same electron configuration as neon. Now, once you have a noble gas electron configuration, you have a full outer shell of 8 valence electrons, and so they're exceptionally stable. So we would expect it to be incredibly hard to remove a third electron from the magnesium ion because that would be breaking up a full valence shell. Okay, so let's look at this problem. It says if you were to examine the successive ionization energies for vanadium, what would you expect to see given that oxidation states 2 through 5 exist for this atom? So for this example, we don't even really need the periodic table. If it tells us that an oxidation state of +5 is available, then we can infer that an oxidation state of +6 is not available. That means that after 5 electrons are lost, we should expect to see a huge jump after the 5th ionization energy. And this actually explains why transition metals can have multiple oxidation states, because each successive ionization energy represents a very small change in magnitude, and so an additional electron is not that difficult to remove until you get to that noble gas configuration. All right, so one more example. It says, which transition metal in period 4 is this? Justify your answer. So you have to make sure when you answer these IB questions that you answer the entire question. So what I want you to do is give me the identity of the metal and a justification for your answer. So pause the video, take a moment to do that. Okay, so as we look at the ionization energy data for the first, second, third, etc. ionization energies, we see slight increases in ionization energy all the way through the 7th ionization energy. Once we go from the 7th to the 8th ionization energy, we see a much larger jump in ionization energy. That tells us that this element, this metal, can lose 7 electrons before gaining its noble gas electron configuration, which tells us that the metal in question is manganese. If we look at manganese, it can lose 1, 2, 3, 4, 5, 6, 7 electrons before it reaches its noble gas electron configuration. So we'd expect to see a very large jump in ionization energy after 7 electrons are lost, which is exactly what we do see. Okay, ionic radius. Now, anions will always have a larger radius than their parent atoms. So in this case, the chloride ion will be larger than the chlorine atom. And the reason is greater electron repulsion. As we add electrons to the atom, we increase the total number of electrons and increase the total amount of repulsion. So the entire electron cloud will spread out a little bit, making the ion bigger. The trend for cations, is the exact opposite. So cations will always be smaller than their parent atoms. So in this case, the sodium ion, or the sodium atom, will be larger because it has one more occupied energy level. When you take that one electron away from sodium, you're removing an entire energy level, so the sodium ion will be much smaller. And next we have a definition, isoelectronic. Isoelectronic, the definition is just 2 different species, whether they be atoms or ions, that have the same number of valence electrons, thus the same electron configuration. So an example here would be the potassium ion and argon. So if we look at the periodic table, when potassium becomes an ion, it loses 1 electron. The potassium atom has 19 electrons, so the potassium ion has 18 electrons, just like argon. So in that case, argon and a potassium ion would be isoelectronic because they have the same electron configuration. And the next thing they like you to do is rank a series of atoms or ions in order of increasing radius. Now, since cations are the smallest species and anions are generally the largest species, we know that the cations will be the smallest and the anions will be the largest. Now, the noble gases generally fit right into the middle. So now we know that either the calcium ion or the potassium ion will be the smallest species. Now, when you have 2 adjacent metal cations in the periodic table, the trend for atomic radius will hold true. So since calcium is 1 box to the right of potassium, it will have a smaller ionic radius than potassium. And when we look at the anions, we know that the anions are larger because they gain electrons. So the more electrons that are gained, the larger the radius will be. So the chloride ion has gained 1 electron, and the sulfide ion has gained 2. So the order of increasing radius will show the calcium ion is the smallest, followed by the potassium ion, with the argon atom in the middle, followed by the chloride ion, and then the sulfide ion. Okay, so in general, with ionic radius, the radius of an anion is roughly twice as big as the radius of its parent atom. And for cations, the radius of the cation will be roughly half the radius of its parent atom. So this is just a visual representation. Okay, now let's talk about reactivity of alkali metals. If you recall, alkali metals are all the metals in group 1. They include lithium, sodium, potassium, rubidium, cesium, and francium. Now the trend in reactivity down the group is one of increasing. And that made little sense. The trend increases going down the group. The reason why has to do with ionization energy. As we go down the group, ionization energy decreases, meaning it's easier to remove an electron from those atoms. So since these metals react by losing electrons, the more easy it is to lose the electron, the more reactive they become. And we'll also talk about the melting point of alkali metals. Now this has to do with the nature of metallic bonding, which we'll talk about a little bit more in Unit 4. But since they're trends in the periodic table, I feel like it's a good idea to talk about it here. So for the melting point of alkali metals, the trend going down the group is that the melting point decreases. And the reason why is because of the shielding effect. As energy levels are added, the metal nuclei will have weaker attraction to the mobile electrons that hold the whole thing together. And again, I will explain metallic bonding in a subsequent unit. But for now, just know that the trend in melting point decreases going down the group for metals. Now let's talk about the reactivity of halogens. So the trend in reactivity of halogens going down the group is that it decreases. And the reason why is because nonmetals, being the exact opposite of metals, actually react by gaining electrons. That means that electronegativity is more important in governing their reactivity. And since electronegativity decreases going down a group, the reactivity of the halogens will also decrease down the group. Now, this time I want to talk a little bit about the activity series, or the relative reactivity of the halogens. So first of all, when halogens are in ionic form in solution, in other words, halide ions, will create clear, colorless solutions, just like water. That's why when you take table salt, sodium chloride, and put it into water, it does not make any kind of color. But elemental halogens each have their own unique color. Fluorine and chlorine are greenish yellow gases. Bromine is a reddish-brown liquid, and iodine is a deep blue violet solution. Solid. You could also keep elemental iodine in solution as well. Now, if it's a solution of elemental iodine, you'll see it written as I2 aqueous because the halogens are diatomic molecules. But if you have a solution of iodide ions, then the solution will be clear. So let's look at some reactions and determine if they will happen. Now, we talked about single replacement reactions in IB Chem 1, and we talked about how some of them will not occur. And we see here we have elemental fluorine reacting with bromide ions. Now, in the atomic world, the ionic form is a more stable form because the ions have 8 valence electrons, whereas the atoms do not. So fluorine and bromine both want to be ions. Now, bromine is already an ion, and the only way that fluorine is going to replace it is if it is more reactive. So take a moment, pause the video, and see whether you think a reaction would occur and what the products of the reaction would be. All right, so first of all, fluorine is more reactive than bromine, so we will indeed see a reaction. So fluorine atoms will replace bromide ions by becoming ions themselves. That should say aqueous. And that'll form bromine liquid. Now, when we perform that reaction, because we're forming elemental bromine, what we will expect to see, oh man, I just screwed that whole thing up. There we go. Is a clear solution becoming reddish or brown. All right, now let's look at this example. And we have liquid bromine reacting with fluoride ions. Now, since bromine is less reactive than fluorine, what we'd actually expect to see is no reaction. And so since elemental bromine is reddish-brown, we would expect to see the solution remain a reddish-brown color because no reaction occurs. Let's look at a couple more. Now we have elemental iodine in aqueous solution reacting with chloride ions. Now iodine is below chlorine in the periodic table, which means it's less reactive, so we would expect to see no reaction. And since elemental iodine in solution will produce a blue-violet solution, we will not expect to see a color change. Move my arrow there. And finally, take a moment, pause the video, and see if you can determine if a reaction will occur between elemental chlorine and iodine ions, and if so, what would the products of the reaction be, and what would you expect to see in terms of color change? Okay, so there goes my arrow again. I gotta get used to this whole undoing thing. We would actually expect to see a reaction because elemental chlorine is more reactive than iodine. And so chlorine will become chloride ions, and we will see aqueous iodine being produced. Now that we see that it is diatomic, so the color change we would expect to see is a clear solution becoming blue as the iodine is produced. Okay. So let's also talk a little bit about the melting point of the halogens. The trend going down the group is that it increases. We can see this because fluorine and chlorine are gases, whereas bromine is a liquid, and iodine in its natural state is a solid. And the reason why is because of intermolecular forces. Now, we'll talk a little bit about this more in Unit 4, like I said, but intermolecular forces will increase as the total number of electrons in the atom increase. So as they have more and more electrons moving down the group, their melting point will also increase because the intermolecular forces are stronger. All right, so summing up, why are these trends different? The alkali metals become more reactive going down because of the trend in ionization energy, and halogens will become less reactive going down a group because of the trend in electronegativity. So a popular multiple choice question on IB tests is they'll give you several pairs of metals and nonmetals and ask you what would be the most reactive pair. So what we're looking here for is the nonmetal with the highest electronegativity and the metal with the lowest ionization energy, or the halogen that's highest in the table and the metal that's lowest in the table. And in this case, fluorine and potassium have the greatest difference, so they would be the most reactive pair. Okay, final trend, period 3 oxide compounds. What happens when the period 3 oxides react with water? So for this, you have to be able to write reactions for these oxide compounds reacting with water. And you have to know what the trend would be concerning their acidity or basicity. So let's look at them one at a time. When sodium oxide reacts, or when sodium oxide reacts with water, I'm sorry, that should say Na2O, reacts with water, we form sodium hydroxide, a basic solution. When magnesium oxide, and that should also say magnesium oxide, I'm sorry I screwed these slides up. When magnesium oxide reacts with water, we'll expect to find magnesium hydroxide. Now these relationships are still true, these reactions are real, but we're actually talking about the oxide compounds and not the elements themselves. And when we look at tetraphosphorus decoxide reacting with water, we see that we form H3PO4. Now we know this is an acid because the compound formula starts with an H. That's actually called phosphoric acid. And when we react sulfur trioxide with water, we form sulfuric acid. And if we were to react elemental chlorine or a chlorine oxide compound with water, we would form hydrochloric acid. So the trend going across period 3 is that the solutions formed from those reactions will become more and more acidic as we go across the period. So sodium and magnesium make basic solutions. Aluminum, right in between magnesium and silicon, will make what are known as amphoteric solutions. That just basically means they could form an acidic or a basic solution, so they're essentially neutral. And then silicon, phosphorus, sulfur, and chlorine will all form acidic solution. And why does this matter environmentally? Well, sulfur dioxide and sulfur trioxide are produced by large-scale industrial processes. So what happens when they're going to react with water vapor in the air? Well, you guessed it. They're going to make acid rain. That is known as acid deposition. We'll talk about that more in Unit 8. But for now, all we need to know is that those sulfur oxide compounds will produce sulfuric or sulfurous acid when reacting with water. All right, and that is it for discussion 2-3 and Unit 2. If you have any questions about this discussion, please bring them to class for the review day.